The countdown has already begun. On October 30th, 2025, a fragment of frozen matter from another star system will brush past our Sun, a silent encounter at just 1.4 astronomical units, where solar heat is no longer gentle radiation but a weapon of raw energy. Imagine this: billions of tons of ancient ice, locked in darkness for perhaps 1,000,000 years, now rushing into a storm of photons intense enough to boil metal if it lingered too long. The Sun does not roar, it simply radiates. But its light becomes a pressure wave, its warmth a field of invisible hammers striking every crystal lattice inside that alien object. In the deep vacuum, heat travels inward like an invasion. Cracks form. Vapor trapped beneath kilometers of frozen crust begins to push, searching for escape. Then, silence breaks. A jet erupts. A plume arcs into sunlight, scattering dust that's never before seen a star. Instruments on Earth and in orbit catch faint spectral lines, a chemical whisper carried across millions of kilometers. Oh, radicals, water breaking apart in sunlight, detected by NASA's Swift telescope months before the real approach. Too early, too far. Something inside this interstellar wanderer is stirring before physics says it should. And as it closes the distance, we begin to wonder what happens when heat and ice, born in different corners of the galaxy, finally meet under the crushing weight of solar pressure. Tonight, we embark on a new journey, where the theme of 3I, Atlas versus the Sun, heat versus ice, under extreme pressure, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map tonight? Let me know where you're listening from and what time it is in your corner of the world. It's always fascinating to see who's joining us from all around the world. Ahead, the story unfolds through faint signals and distant heat. Swift's early detection of evaporating water far from the Sun, a puzzle hinting that internal vapor pressure or cracking ice may be reshaping the comet before the real encounter even begins. The trajectory of the interstellar object, designated 3I, Atlas places it on a direct and unforgiving course, a celestial rendezvous with our Sunday. On the 30th of October, 2025, it is projected to reach a perihelion of approximately 1.4 astronomical units. This is not a distant cold passage. It is a plunge into a stellar furnace. The central question, the hook upon which all observation hangs, is one of survival. Can a primordial iceberg, a wanderer through the galactic void for billions of years, possibly endure a close encounter with a star's ferocious energy? Its composition, forged in an alien system and tempered by the profound cold of the interstellar medium, now faces its ultimate test. According to current models of cometary science, such an object, predominantly composed of water ice, carbon dioxide, and dust, should undergo violent outgassing and structural stress as solar radiation heats its surface. The thermal and pressure models predict a powerful thermal gradient, sufficient to strip away surface layers in a process akin to planetary scale, sandblasting, potentially creating a transient faint coma. The orbital data, meticulously refined by trajectory analysis groups throughout late September 2025, all converge on this single, fiery point in space and time. The object's early activity at great solar distance and its velocity of approximately 58 kilometers per second suggest a volatile nature, one that should be highly susceptible to solar influence. But what if our models, built upon the fragile comets of our own Oort cloud, are insufficient to describe an artifact from another star? This leads us to a more speculative hypothesis. What if 3I Atlas possesses a unique internal architecture, one engineered by the unknown physics of its origin? Perhaps its icy mantle is not a solid slab, but a superporous, fractal matrix that absorbs and dissipates heat with the efficiency of the ceramic tiles on a space shuttle, acting as a natural thermal shield. Or, more profoundly, it may harbor a core of metallic carbon alloys, a super-strong skeletal structure that provides immense tensile strength against thermal shock. We might even envision a self-regulating cyclical system where escaping carbon dioxide gas continually refrees on the sun-facing side, creating a dynamic, self-healing crust. Is it possible we are not observing a simple comet, but a vessel of sorts, designed for resilience in a universe of extremes? The confrontation will likely unfold in distinct, observable stages. The first level is one of superficial shedding. The outermost layers, perhaps a dusty crust accumulated over eons, are violently ejected, creating a coarse, dusty tail, while the fundamental nucleus remains intact. This is the expected behavior, the standard narrative of a comet under duress. But what if the stripping away of this veneer reveals not a predictable core of pristine ice, but something far more structured? This brings us to the second level of analysis: circumferential fracturing. Under immense thermal pressure, the object's shell could develop a network of cracks, fissures that snake around its circumference. From these wounds, jets of gas and dust would erupt not randomly, but in organized, asymmetrical plumes, stretching for hundreds of thousands of kilometers into the void. Such a spectacle would indicate a complex internal layering, a defined crust, and a pressurized interior. Are we witnessing the death throes of a simple ice ball, or the controlled venting of a more complex geological entity? The third, and most catastrophic, level is that of interlayer disintegration. Here, the core itself fragments into multiple pieces. Each new fragment, with its own exposed volatiles, would ignite, activating a new cometary nucleus and spawning a cluster of tails pointing in divergent directions. It would be a brief, brilliant, and terminal fireworks display. Yet, even in its destruction, it would provide the ultimate data set. Does fragmentation signify a fundamental structural weakness, or could it be a deliberate dispersal mechanism, a biological or technological strategy we have yet to comprehend? The implications of 3I Atlas surviving this thermal ordeal are profound. If it emerges from perihelion largely intact, we would have the first opportunity to calibrate a thermal durability scale for interstellar ice. This would revolutionize our approach to future exploration. It opens the door for probes designed to actively sunbathe similar interstellar objects, using their evaporating ices as a readily available source of propellant. But to harness such a resource, we must first understand the trigger mechanism that awakens these distant travelers. What mysterious force begins the outgassing process long before solar heating becomes intense? This very mystery was hinted at by data from a different eye in the sky. Months before its fiery trial, the NASA Swift Observatory, in August and September of 2025, detected the spectral signature of the hydroxyl molecule at a remarkable distance of nearly 3 astronomical units from the sunday. This is the telltale sign of water vaporization, an activity that should be dormant at such a cold and distant point. Conventional science suggests that solar radiation is the sole driver of such sublimation. Yet here, 3I Atlas was already stirring, already bleeding water vapor into the vacuum, activated by an unseen hand. The Swift data presents an anomaly that challenges the very premise of a passive, sun-driven object. What catalyst, internal or external, could possibly be at work, initiating a process that defies the conventional thermal models of our solar system? In the early autumn of 2025, as the Swift satellite diligently scanned the heavens in the ultraviolet and optical bands, it recorded a spectral signature that would quietly challenge our understanding of cometary behavior. At a distance of approximately 3 astronomical units from the Sun, a point well beyond the typical snowline, where water ice is expected to remain dormant, the unmistakable fingerprint of the hydroxyl molecule began to emerge. This was not the violent outburst of a comet in its death throes, but a gentle, premature awakening. According to current models, this early activity could be attributed to the presence of amorphous ice, a glassy, non-crystalline form of water that can release energy and transition to a crystalline state at surprisingly low temperatures, a process known as exothermic crystallization. This gentle heating could theoretically explain the subtle increase in the comet's overall brightness, synchronized with the OH detection without a full-scale cometary eruption. But if the transformation of amorphous ice is a universal process, why do we not witness this pre-activation phase in every comet that ventures inward from the Oort cloud? This anomaly invites a more speculative hypothesis. Perhaps the comet's nucleus is not a simple, homogeneous ball of ice and dust, but a far more intricate structure. Imagine a cosmic sponge, riddled with a network of microscopic capillaries and pores, a labyrinthine architecture that traps volatile gases like water vapor. Within this dark, cold matrix, only the most minimal thermal nudge, a faint whisper of solar energy from a distant sun, would be required to initiate a slow, deliberate leakage of hydroxyl. Or, consider an even more profound possibility, that the comet carries within it an exotic catalyst, a material not native to our solar system. This interstellar hitchhiker, acquired during the comet's long journey through the galactic medium, could act to lower the activation energy required for water ice to sublimate, effectively tricking the ice into believing it is in a warmer environment than it truly is. What unknown chemistries, forged in the nurseries of other stars, might be slumbering within these primordial wanderers? The data from Swift presents a narrative of escalating complexity, a drama unfolding in 3 distinct acts. The first level is this gentle activation, a mere sigh from the comet that generates a tenuous, diaphanous coma and a faint, almost imperceptible gas tail. It is the initial stirring of a slumbering giant. The second level suggests the opening of these hypothetical capillary valves. As the nucleus rotates, we might expect to see localized jets, small geysers of gas and dust whose intensity oscillates with the comet's spin, tracing the opening and closing of these subsurface vents. The final, most dramatic level would be the explosive release of built-up pressure. Trapped gases, no longer able to vent gradually, could violently blow off entire surface plates, resulting in powerful outbursts that could measurably alter the comet's rotation, a testament to the powerful forces churning within its heart. Could the seemingly placid approach of a comet towards the sun conceal a violent, subsurface pressure cooker waiting to burst? The implications of such early water release extend far beyond academic curiosity. A comet that activates at 3 astronomical units, well before the intense heat of the inner solar system begins its work, presents a tantalizing prospect for the future of deep space exploration. It suggests the existence of natural way stations, reservoirs of water that could, in theory, be harvested by spacecraft venturing into the void. Water, after all, is not merely a source of life, but a source of rocket fuel when split into its constituent hydrogen and oxygen. The ability to map and predict these early activating comets could one day transform them from objects of study into vital resource depots, turning the emptiness of space into a landscape dotted with cosmic oases. But does this vision of celestial resource extraction force us to reconsider the very nature of these bodies, from inert relics to dynamic, active participants in the solar system's economy? Yet, the fundamental mechanism driving this premature outgassing remains shrouded in mystery. Is it a simple, uniform process of internal vapor pressure building within the ice as it warms, or is it a far more chaotic and structural phenomenon? The spectral data reveals that the gas is escaping vigorously, yet its distribution is anything but even, hinting at localized sources and a complex internal architecture. This leads us to the next, critical question. Is the driving force a steady, accumulating internal steam pressure, Or is it the catastrophic failure of the nucleus itself through a process of pressure cracking, where thermal stresses create fractures that vent the interior to the vacuum of space? The surface of the interstellar visitor, designated 3I Atlas, is not a placid expanse of inert ice, but a dynamic, breathing landscape. We observe powerful, yet patchy and sporadic, jets of gas erupting from its fractured nucleus. The fundamental question we must confront is the origin of these outgassing events. Are they driven by the internal steam pressure of volatile ices, sublimating in the deep vacuum of space, or are they the result of tidal or thermal stresses, creating a network of fissures, ventilating the interior? Mainstream planetary science suggests a model of heat conduction. As the object rotates, its surface is unevenly heated by the distant sun. This thermal energy penetrates the crust, triggering the sublimation of ices trapped within a porous matrix. According to current models, the resulting water vapor pressure builds in subterranean pockets until it finds a path of least resistance, forcefully venting into space. This is a predictable, almost mechanical process, governed by the laws of thermodynamics and material strength. Yet, the data presents an anomaly. Spectral analysis of the gas jets, particularly those recorded in late September 2025, reveals an asymmetric outflow. The emission lines fluctuate in intensity, not merely with the object's distance from the Sun, but in precise concert with its rotational phase. This is a signature more consistent with gas escaping through specific, fixed vents like geysers on a cosmic scale, rather than a uniform seepage from a homogeneous substrate. Could a simple pressure buildup account for such a sharply defined and rhythmically timed exhalation? This leads us to a more speculative hypothesis. Perhaps 3I Atlas possesses a unique internal architecture, a honeycomb of pressurized chambers. Within this cryptic lattice, volatile ices are sealed away. When a local temperature threshold is surpassed, a chamber does not merely leak, it violently decompresses, acting as a natural pressure relief valve. An alternative, yet equally compelling proposition, is that the object's crust is composed of a patchwork of materials with different thermal properties. These thermal tiles expand and contract at varying rates, generating immense differential stresses that methodically crack the surface open, layer by layer, creating new vents for the pent-up gases. Is the object we are observing not a simple primordial iceberg, but a complex piece of celestial engineering, riddled with intentional chambers and stress-managed fracture points? To comprehend this system, we must analyze it across escalating levels of complexity. The first level is that of simple fissure breathing. Here, gas escapes through stable, individual cracks in a relatively steady and predictable flow. This is the baseline activity, the quiet respiration of a world in equilibrium with the solar energy it receives. But is any celestial body ever truly in a state of stable equilibrium? The second level introduces a crack network. Imagine not a single fissure, but a web of interconnected fractures, a labyrinth carved into the ice. When pressure builds in one region, it does not vent from a single point, but is channeled through this network, illuminating the entire grid like a sprawling neon sign flickering to life in the void. This would explain the sudden, coordinated brightening across disparate regions of the nucleus, a phenomenon difficult to reconcile with isolated geysers. What force, then, is capable of weaving such an intricate and responsive web beneath the surface? The third and most dramatic level is that of chamber collapse. This is not a gentle venting, but a catastrophic structural failure. A large subsurface cavity, its structural integrity compromised by sustained outgassing, implodes. The result is a silent explosion, a massive, impulsive jet of material that does not produce a sound but delivers a tangible physical reaction. The transfer of momentum from such an event is significant enough to impart a nudge, a minute but measurable change in the object's rotation and trajectory. We are no longer observing mere outgassing, but a geological event that alters the very state of the body. Could such internal rearrangements be a natural process, or does it hint at a hollowed interior, now undergoing a fatal structural failure? Understanding this hierarchy of outgassing is not merely an academic exercise, it is the key to any future attempt at contact. To design a landing mission, we must know where to set down a delicate probe. We must learn to avoid these breathing arteries, these active volcanic maws, to prevent the destruction of our instruments and, more importantly, to avoid contaminating or destroying the very nucleus we seek to study. A successful mission would be one that gently alights upon a quiescent region, allowing us to sample pristine material from an interstellar object for the first time. But does this visitor's violent and unpredictable nature suggest it does not wish to be sampled? The chemical story written in the light of its escaping gases presents another layer of mystery. It is a story that forces us to look back at the two previous interstellar messengers. The first, 1I Oumuamua, detected in 2017, was a dry, enigmatic shard, showing no discernible coma or tail, its composition a subject of intense debate. The second, 2I Borisov, arrived in 2019 as a familiar, yet alien, comet, rich with carbon monoxide. Now, 3I Atlas shows us a spectrum that lies between these two extremes, a hybrid, possessing volatiles but in a pattern and proportion that defies easy categorization. It does not merely present a third data point, but suggests the existence of a vast and diverse interstellar chemical spectrum. What, then, does this trilogy of visitors tell us about the true variety of worlds being forged between the stars? In the brief but illuminating history of interstellar interlopers, each visitor has presented a distinct cosmic passport. The first, 1I Oumuamua, arrived in 2017 as a silent, enigmatic traveller, devoid of the classic cometary coma and exhibiting a dry, rocky composition that defied easy categorization. Its passage was marked only by a subtle, non-gravitational acceleration, a ghostly push that left no visible trail of outgassing. Then, in 2019, came 2I Borisov, a veritable archetype of a comet, erupting with a vigorous halo of dust and gas, its spectrum rich with carbon monoxide, a familiar song from a foreign star. Now, 3I Atlas positions itself between these two extremes, a chemical intermediary that refuses to conform to our nascent binary classification. It is neither entirely dry nor wildly volatile, but something in between a third, hybrid chemical score in the growing symphony of interstellar objects. Could this be the missing link, a Rosetta Stone written in the language of ices and dust, waiting to be deciphered? According to current models of planetary system formation, such diversity is to be expected. Protoplanetary disks, the swirling cradles of worlds, are not chemically uniform. Their composition is a function of temperature and radiation, creating distinct zones where different ices can condense. An object forming in the cold, distant reaches of such a disk would be rich in volatile compounds like carbon monoxide, much like 2I Borisov. Conversely, a body that spent its formative years closer to the heat of its star would be stripped of these light ices, leaving behind a drier, more refractory core, a possible explanation for the nature of Oumuamua. 3I Atlas, with its intermediate activity, could simply be a sample from a transitional region, a piece of a disk that experienced a moderate thermal history. Its composition would then be a straightforward average of its birth environment, a fossilized record of a specific annulus around a distant sun. But what if the story is not so simple? What if this object is not a pristine sample from a single location, but a composite, a geological tapestry woven from multiple epochs and environments? This leads us to a more speculative hypothesis, that 3I Atlas is not a monolithic fragment, but a cosmic palimpsest, It could be a collage of material from multiple preplanetary disks, a single object assembled from the wreckage of different stellar nurseries, carrying within it a hybrid chemical signature never before seen. Alternatively, its history may be one of profound transformation. Imagine a core that was once scorched, baked dry in the intense heat of its youthful star, its volatile contents completely lost to the void. Then, through a dynamic upheaval, it was flung outwards into the frozen outskirts of its system, or even into a passing molecular cloud. There, in the deep cold, it could have been recoated, resurfaced, with a new mantle of exotic ices condensed directly from the interstellar medium. This would create a layered object, a dry, ancient heart, shrouded in a cloak of recently acquired frost. Is 3I Atlas such a twice-processed relic, its current activity merely the sublimation of its most recent superficial acquisition? The initial spectroscopic data from August and September 2025 provide the first clues to test these ideas. The spectra of 3I Atlas are neither blank like Oumuamua's nor overwhelmingly rich like Borisov's. They are intermediate, hinting at the presence of water, carbon monoxide, and carbon dioxide in unusual ratios. Its morphology speaks to this compromise. The coma and the incipient tail are present, confirming activity, yet they lack the untamed, wild effervescence that characterized Borisov's brilliant passage. The comet is active, but restrained. Furthermore, photometric observations reveal that its dust grains are darker than those of typical solar system comets, suggesting a different mineralogical makeup or a higher concentration of complex, carbon-rich compounds. Does this darker dust imply a formation environment richer in carbon, or a longer exposure to interstellar cosmic rays that have polymerized its surface? A first-level analysis suggests a neutral, multi-phase mixture of gas and ice is responsible for its moderate activity. In this conventional view, the object contains a blend of different volatiles, frozen together in a porous matrix. As solar heating penetrates the surface, these ices sublimate at different rates, releasing gas and dragging dark dust grains along in a predictable, if complex, dance. The observed activity would be the sum of these individual contributors, a straightforward physical chemistry experiment playing out on a cosmic scale. The non-gravitational acceleration, a faint echo of the force that propelled Oumuamua, could be explained by a slightly asymmetric outgassing pattern from this mixed reservoir. But does a simple mixture adequately account for the peculiar dominance of certain molecules and the distinct darkness of the dust? This leads to a second, more nuanced level of interpretation: hybridization. The data increasingly point not to a balanced mix, but to a stratified or heterogeneous interior, where carbon dioxide emerges as the dominant volatile, with water ice playing only a minor, leaking role. This is a significant departure from the water-dominated chemistry of our own solar system's comets. Such a CO2-rich composition could indicate formation in an extremely cold region of a protoplanetary disk, a place where carbon dioxide ice was more abundant than water ice, or where water was locked away in less volatile forms. The object would then be a native of the deep freeze, a testament to the chemical diversity of cosmic nurseries. Yet, if it is a resurfaced object, this CO2-rich layer could be the newly acquired frost, the final coating applied in the interstellar void. How can we distinguish between a primordial composition and a late-stage veneer? Pushing the speculation further necessitates a third-level analysis, a phase separation scenario. Perhaps the internal structure of 3I Atlas is not uniform. Its core may consist of a large, dry, and cohesive component, a fragment of that previously baked planetesimal. This inert core would act as a thermal and mechanical barrier, distorting the flow of gas, sublimating from the icy layers above or around it. The jets of gas and dust would not emanate symmetrically from the nucleus. Instead, They would be channeled, focused, and deflected by this irregular, dry interior. This could generate a much more significant and complex non-gravitational force than expected, a substantial rocket effect originating from its lopsided internal geography. The observed activity would then be merely the visible manifestation of a hidden, intricate architecture. Is the gentle push we measure merely the surface expression of a profound internal disequilibrium? The profound implication of 3I Atlas lies in this very chemical diversity. Each interstellar object is a new entry in a cosmic library, expanding our dictionary of possible planetary ingredients. 1I Oumuamua gave us one word. 2I Borisov gave us another, quite different. Now, 3I Atlas provides a third, more complex term. This growing vocabulary is crucial for the future. With the upcoming legacy survey of space and time from the Vera C. Rubin Observatory, we expect to find dozens, perhaps hundreds, of such interstellar visitors. The chemical spectrum of 3I Atlas, with its blended and puzzling features, provides a vital training set for machine learning algorithms that will be tasked with the rapid classification of this new population. It teaches our algorithms to look for nuance, for intermediates, for the strange hybrids that may be the most common products of galactic evolution. But can any automated system truly comprehend the layered history each of these icy messengers carries? The initial ground-based spectra have set the stage, but they are limited, filtered through Earth's turbulent atmosphere. To truly read the chemical text of this visitor, we must turn our eyes to the vacuum of space, to an instrument designed to perceive the faint molecular whispers that ground-based telescopes cannot hear. The data from the first observations were merely the prologue. The next chapter promises to reveal the protagonist of this chemical drama, a molecule whose surprising dominance could rewrite our understanding of interstellar ice. What definitive signature would the most powerful spaceborne observatory ever built to detect when it finally turned its golden mirror towards the wandering 3I Atlas? The data stream is a river of cold light, a cascade of photons captured and translated by the golden hexagons of the James Webb Space Telescope. In the silent, airless void, it has fixed its gaze upon a stellar nursery, a swirling cloud of gas and dust where new solar systems are coalescing in the dark. The initial analysis of the mid-infrared wavelengths, a domain invisible to human eyes but laid bare to Webb's instruments, reveals a spectral narrative that is both clear and confounding. The expected signature of water, the ubiquitous solvent of life as we know it, is present, but it is a mere whisper, a faint spectral line against the cosmic background. Dominating the spectrum is an unequivocal, robust signal of carbon dioxide. This is not a mere trace. It is an overwhelming presence, a chemical shout where water only murmurs. The cloud's cold fringe, the region where gases freeze onto the surfaces of interstellar dust grains, appears not as a reservoir of water ice, but as a vast repository of frozen carbon dioxide. What does it mean for the genesis of a world when its foundational ices are not of water, but of a different chemistry entirely? According to current astrophysical models, the composition of ices in a molecular cloud is a direct function of temperature and pressure. Water, with its higher freezing point, is expected to dominate the inner, denser regions, while more volatile molecules like carbon dioxide condense only in the colder, outer reaches. The strong carbon dioxide signal from the James Webb Space Telescope in July 2025 could simply be a palm reservoir, testament to the profound cold at the edge of this particular cloud, a perfectly natural outcome of local thermodynamic conditions. The faint water signal would then logically indicate that the water has largely remained in the gas phase, unable to freeze out in this specific thermal environment. The absorption and emission models further support this, pointing to the presence of large, dark dust grains with low albedo, perfectly consistent with the observed low luminosity and the efficient formation of carbon dioxide ice mantles. It is a clean, rational explanation, one that fits neatly within the established paradigms of interstellar chemistry. But does the sheer dominance of carbon dioxide, its spectral line so starkly overpowering the fundamental molecule of life, truly fit within our comfortable models? Or does it hint at a more exotic form of matter taking shape in the darkness? This leads us to a more speculative frontier. Perhaps we are not witnessing simple carbon dioxide frost. The data, with its suggestion of large, dark grains, could be interpreted as evidence of something far more structurally complex. One hypothesis posits the existence of a vitrified carbon dioxide coat. Imagine a nucleus of silicate dust, upon which carbon dioxide has not merely frozen, but has formed a supercooled, glass-like amorphous solid. This layer would not be a simple frost. It would be a hard, continuous shell, a cold mirror that reflects energy with an efficiency unknown to crystalline ices. Such a structure would explain the anomalous stability and the low emission profile, acting as a perfect insulator and a shield. An even more exotic proposition involves the formation of unique clathrate hydrates. These are not the water-based clathrates found on Earth, trapping methane or carbon dioxide in cages of water ice. Instead, this would be an inverted architecture, a carbon dioxide clathrate, where the matrix of the crystal itself is made of solid carbon dioxide, trapping other, rarer molecules within its unfamiliar lattice, a molecular prison of a type never before seen within our own solar system. Could the fundamental building blocks of planets be constructed from ices whose very atomic architecture defies our terrestrial experience? This initial layer, whether a simple frost or a more complex vitrified shell, serves as the first line of defense for the nascent protocometry body. It is a shield, a barrier against the subtle erosive forces of the interstellar medium. The carbon dioxide mantle sublimates slowly, evenly, providing a steady, gentle outflow of gas that does not disrupt the core's integrity. This process grants the object a remarkable longevity and stability as it drifts through the cloud. Its low albedo allows it to hide in plain sight, a dark, cold entity conserving its volatile materials over eons. This is the first level of analysis, the carbon dioxide as a protective cloak, a guarantor of a quiet, enduring existence in the cradle of star formation. But what happens when this cloak is not just a passive barrier, but an active participant in the thermal dynamics of the core? We must then open a new window into this process. The carbon dioxide ice, particularly in its pure, solid form, possesses unique infrared properties. Its spectral bands are not just identifiers, they are conduits. The strong carbon dioxide features detected by Webb could act as a channel, a pipeline for thermal energy. Photons carrying heat from the nascent protostar at the cloud center or from interstellar radiation fields are efficiently absorbed by the carbon dioxide ice. This energy is not merely reflected or stored at the surface. It is transmitted inward, conducted along the molecular bonds of the ice layer deep into the heart of the growing planetesimal. This internal heating, subtle though it may be, occurs within an environment that is still profoundly cold. The result is a cold fracture, a term describing the creation of internal stresses and thermal gradients, not from warmth, but from the very delivery of cold. This is the second level, the carbon dioxide band as a thermal waveguide, creating a delicate and potentially unstable internal architecture. Is the core of this object a homogeneous block of ice, or is it a stratified stress structure, silently building tension under its dark, insulating coat? The final, most dramatic level is the inevitable flip side of this stratified stability. The carbon dioxide layer, for all its strength, is not permanent. A gravitational perturbation, a collision with a neighbor, or the slow, insistent warmth of a newly ignited star could provide the trigger. When the pressure and temperature cross a critical threshold, the vitrified carbon dioxide shell does not just sublimate, it shatters. This is the moment of inversion, the protective layer becomes a vulnerability. With the carbon dioxide shield ruptured, the volatile species trapped beneath, including the water ice that was previously only a whisper in the spectrum, are suddenly exposed to the vacuum. They erupt. This is not a gentle outgassing, but a violent decompression, a geyser of pent-up molecular force. The water, once hidden, bursts forth like a released spring, transforming the quiet, dark planetesimal into an active, brilliant comet. The James Webb data, then, may be showing us not a static picture, but a prelude to a future cataclysm, a population of dormant worlds, their true aqueous nature masked, waiting for the moment of their unveiling. How many of the comets we see flashing through our own skies were born under such a deceptive carbon dioxide blanket? This chemical hierarchy, with carbon dioxide as the primary language of interstellar ice rather than water, forces a profound reconsideration of cosmic chemistry. If this is a common pathway for planetary formation elsewhere in the galaxy, then the very definition of a habitable zone may need revision, focusing not just on liquid water, but on the complex interplay of carbon dioxide and water ices during planetary accretion. This perspective also opens a startling practical vista. If carbon dioxide is the dominant frozen volatile in the cold storage of space, then the future of deep space exploration and infrastructure could be rewritten. Orbital fuel depots and interstellar waste stations, the essential pit stops for humanity's expansion into the cosmos, would not need to seek out water-rich asteroids as their primary resource. Instead, they could prioritize these carbon dioxide-rich bodies. The chemistry of carbon dioxide, through sophisticated catalytic processes, could be harnessed to produce methane and oxygen, the very lifeblood of rocket propellant and life support. A green fuel cycle, sustainable and efficient, could be built not on water, but on the carbon dioxide that currently appears as an anomaly in our data. Are we looking at a cosmic quirk, or are we witnessing the blueprint for the future fuel depots of interplanetary civilization? Yet, the story of anomalous chemistry in small bodies does not end with the silent, cold ices observed from a distance. What happens when we turn our most powerful ground-based eyes upon a known visitor, a comet that has already ventured into the inner solar system, and find its atmosphere speaking a language even more unexpected? If the frozen outskirts of a stellar nursery can conceal a dominance of carbon dioxide, what other chemical secrets are written in the faint light of a comet's tail, waiting to be deciphered by the next generation of observatories? The void between stars is not truly empty, but a realm of frozen potential. Within the deep chill of molecular clouds, where temperatures hover just a few degrees above absolute zero, simple ices of carbon, hydrogen, oxygen, and nitrogen accumulate on microscopic grains of silicate dust. This is the classical nursery of a comet, a pristine repository of the early solar, the system's most basic ingredients. We have long understood these distant objects as time capsules, their chemical inventories limited to these volatile compounds, their structures defined by the gentle agglomeration of cosmic snow. Yet, the universe has a tendency to complicate our most elegant models. In the fading light of a distant comet, a new signature has been found, one that whispers of a more violent and complex origin. The Keck Observatory, with its formidable light-gathering power, has detected the faint, spectral fingerprints of nickel and the cyanogen radical within the comet's coma. These are not the expected visitors in this frozen domain. According to current models of cometary formation, the nucleus is a conglomerate of ices and dust, a dirty snowball assembled in the quiet, cold outskirts of the protoplanetary disk. The detection of the cyanogen radical, a simple carbon-nitrogen molecule, fits neatly within this paradigm. It is a known constituent of cometary comae, likely a fragment released from the breakdown of more complex organic polymers or hydrogen cyanide ice within the nucleus. Its presence is a testament to the simple photochemistry driven by solar radiation, a process we have observed countless times. The volatile ices warm, sublimate, and are broken apart by the sun's energetic photons, creating a temporary atmosphere of simple molecules and radicals. This is the established, predictable life cycle of a comet. But what of the nickel? The presence of neutral and singly ionized nickel atoms presents a profound anomaly. In our conventional understanding, metallic elements like nickel are locked away within the rocky, refractory dust grains embedded in the ice. They should only be released in significant quantities under intense heat, such as when a comet fragments near the Sun or when dust grains are vaporized in the inner solar system. Here, however, the nickel spectral lines appear faint but distinct, suggesting a steady, low-temperature release far from the Sun's intense warmth. How does a metal with a vaporization point exceeding 2,700 degrees find its way into the gaseous coma of a distant, frozen object? Could it be that the very ice itself holds a secret, not of gentle accumulation, but of a cataclysmic inheritance? One hypothesis ventures that this comet is not merely a product of our local solar nursery. Its core may contain a more exotic material, a legacy of a stellar death that predates our own Sun. Within its frozen matrix, nanoparticles of metallic nickel, forged in the heart of a supernova and seeded into the interstellar medium, could be suspended. These minute specks of pure metal, encased in the water and carbon dioxide ices, would act as a slow-release reservoir. As the water ice sublimates in the gentle heat of the approaching Sun, these nanoscale particles could be directly exposed to the vacuum of space and the solar wind, their atoms sputtered away or released through processes we do not yet fully comprehend. Alternatively, the comet's long elliptical orbit may have once carried it through a localized interstellar cloud, rich in metallic dust, a cosmic brush that left a faint, catalytic stain upon its icy surface. Is it possible that we are not observing a simple solar system object, but a celestial archaeologist, carrying within it the elemental debris of a long-dead star? The data, captured in the high-resolution spectra from September 2025, is unambiguous yet cryptic. The faint signals of nickel-1 and nickel-2, alongside the weak but persistent cyanogen lines, paint a picture of a low-temperature metal release mechanism that defies our current thermodynamic expectations. This is not the signature of a hot, active body, but of a cold one engaged in a subtle and complex chemistry. The concurrent presence of the cyanogen radical suggests that this nickel is not an isolated contaminant. It exists within a chemical environment that includes simple, organic networks. The two detections may be separate threads, or they may be intrinsically linked, parts of a single, larger puzzle written in the faint light of the coma. At the first level of analysis, we can interpret this as a simple, physical leakage. Atoms of nickel are slowly escaping their icy prison, perhaps from the surfaces of those hypothesized nanoparticles. The cyanogen radical acts as a mere indicator, a signpost pointing to the presence of simple organic chemistry occurring in parallel. In this view, the comet is a passive object, its composition a straightforward reflection of its components. The nickel is a tracer, a fossil element that tells a story of origin, while the cyanogen is a product of the ongoing, sun-driven photochemistry. But if the process is so simple, why does the ratio of these elements, and their behavior over time, not align with models of passive sublimation? What if the release is not passive at all, but the result of a more active catalytic interaction? This leads us to the second level of analysis, the concept of reactive clusters. On the complex, porous surface of the nucleus, these nickel atoms may not exist in isolation. They could form tiny islands or clusters on the ice dust grains. Such metallic clusters can act as powerful electron donors and acceptors, creating localized sites of intense chemical activity. The presence of these metallic islands could alter the very color and light absorption properties of the cometary dust, making it a more efficient trap for solar energy and accelerating the sublimation of surrounding ices in a feedback loop we have not previously accounted for. The surface, then, is not a uniform blanket of ice, but a patchwork of chemically distinct domains. Could the faint nickel signature be the visible emission from a vast, invisible landscape of electron exchange and surface catalysis, turning the entire comet into a low-temperature chemical reactor? Pushing further into speculation, we arrive at the third level, the realm of microcatalysis. If nickel clusters are present and active, their influence may extend far beyond altering physical properties like color. They could be initiating entirely new chemical pathways within the coma itself. In industrial chemistry on Earth, nickel is a renowned catalyst for reactions involving carbon and nitrogen, facilitating the formation of more complex molecules from simple precursors. Within the tenuous gas of the coma, the same principles could apply on a microscopic scale. The cyanogen radical, rather than being a mere byproduct of ice destruction, could be an intermediate in a catalytic cycle, its presence sustained or even enhanced by the very nickel atoms we have detected. This nickel could be acting as a factory, transforming simple carbon monoxide and nitrogen molecules into the building blocks of more complex organics. What if the faint spectral lines of nickel and cyanogen are not just co-inhabitants of the coma, but partners in a silent, ongoing synthesis, a chemistry we thought was impossible in the near vacuum of space? This prospect forces a profound reconsideration of the cometary environment. If the surface of a comet can host such sophisticated metal-catalyzed chemistry, then we must view it not as a simple icy body, but as a cold chemical workshop. Its porous interior, shielded from harsh radiation, and its dynamic coma, exposed to stellar winds and light, could provide a unique environment for prebiotic synthesis. The conditions are vastly different from a warm terrestrial pond, but the potential for complexity is no less significant. Within these frozen laboratories, the fundamental reactions that lead to the precursors of life, the nucleobases, the amino acids, could be proceeding not by chance, but guided by the catalytic properties of stardust metals. Are we therefore looking at a mechanism by which the universe seeds itself with chemical complexity, using comets as its distribution network? Does this explain the apparent ease with which the basic ingredients of life appear on newborn worlds? The detection of nickel and cyanogen by the Keck Observatory thus opens a door not merely to a new cometary anomaly, but to a new way of perceiving these ancient wanderers. They are no longer simple archives of primordial ice, but dynamic, chemically active worlds. Their interiors may be laced with the catalytic remnants of supernovae, and their atmospheres may be sites of a chemistry far richer than we imagined. The faint light we analyze carries the signature of processes that could be fundamental to the emergence of chemical complexity throughout the galaxy. But to understand the true nature of this workshop, we must move beyond its chemical inventory and comprehend its physical scale and structure. For the processes unfolding on its surface and within its coma are ultimately governed by the fundamental force that binds it all together, gravity. How does the sheer mass and size of this object shape the very phenomena we are now beginning to decipher? The Vera C. Rubin Observatory's legacy survey of space and time has delivered a crucial measurement, one that fundamentally reclassifies the object we know as 3I Atlas. It is no longer a mere speck of interstellar flotsam. With a nucleus diameter of approximately 11 kilometers, it is a micro-world in its own right, a solitary island adrift in the galactic sea. This substantial size, derived from meticulous analysis of pre-discovery imagery and the object's photometric light curve throughout the first half of 2025, forces a recalibration of our expectations. The calculation, assuming a dark albedo typical of primordial Kuiper belt objects, provides the first reliable constraint on its gravitational field, however faint that field may be. This is the gateway to understanding its true nature, for an 11-kilometer body possesses just enough gravity to begin dictating terms to the very substance it ejects. Could this modest gravitational pull be the architect of the coma's subtle and peculiar morphology? According to current models of cometary physics, The primary driver of activity is the sublimation of volatile ices. As sunlight warms the nucleus, ices turn directly to gas, creating an outflow that drags dust particles along with it. For a small nucleus, this process is a clean escape. The weak gravity is easily overcome. For an 11-kilometer body, the equations shift. The escape velocity, while still low, is no longer negligible. Scientists suggest this could lead to a filtering effect, where only the finest dust grains achieve full escape velocity, while larger, heavier particles succumb to the nucleus's gentle tug. This would result in a coma enriched with coarser, heavier grains, a dusty shroud held in a tenuous embrace. But does this conventional dust filtering mechanism fully explain the persistent, cloud-like nature of the coma, which lacks the sharp, dynamic features of a typical comet? This leads us to a more speculative hypothesis. What if this soft gravity does more than just filter dust? What if it allows for the temporary retention of an entire, ethereal exosphere of dust? A suspended halo, where particles are continuously lifted by outgassing pressure, only to fall back in a slow, perpetual drizzle, creating a dynamic equilibrium, a fog bank enveloping a miniature world. This would be a landscape unlike any we have observed in our own solar system, a realm where dust motes dance in a slow-motion ballet dictated by the faintest of gravitational melodies. Is the coma of 3I Atlas not a simple plume of ejecta, but a transient, gravitationally bound atmosphere in its own right? The estimated size also allows us to calculate the precise vapor pressures required to liberate dust from this weak gravitational grip. We can model the activity not as a single event, but as a layered phenomenon, a hierarchy of eruptions. At the first level, a gentle breeze of outgassing may be sufficient to lift the smallest particles, but only the largest and most porous grains break free, creating a tail of coarse, pebbly material. This would be a slow, persistent leakage, not a violent eruption. Yet, if the activity is merely a gentle breeze, why does the coma appear so structurally complex, hinting at processes far more intricate than simple dust release? This brings us to the second level of activity. Consider the possibility of gusty outgassing, sudden and localized jets of increased pressure. These gusts could provide just enough thrust to launch a cloud of medium-sized particles on shallow, suborbital trajectories. These particles would achieve a temporary escape, only to have their brief moment of freedom curtailed as they arc back down to the surface, tracing silent, ballistic paths in the vacuum. This could create a suspended ring or shell of dust, a toroidal cloud hovering just above the nucleus, a permanent, orbiting haze born from the rhythm of the comet's own intermittent breathing. Could the faint, extended halo glimpsed in some observations be the signature of this gravitational entrapment, a swarm of particles forever falling but never quite landing? And then there is the third and most dramatic level, the shedding of layers. If outgassing occurs from a subsurface reservoir sealed beneath a fragile crust, the resulting pressure need not simply push dust grains apart. It could overcome the tensile strength of the nucleus material itself. The force of the expanding gas would then not merely eject dust, but would pry loose entire plates of the surface, peeling them away in a single, catastrophic sheet. This would be a form of exfoliation on a monumental scale, where the victory of vapor pressure over gravity results not in a stream of dust, but in the wholesale removal of the comet's skin. What violent, transformative events might lie beneath the seemingly placid exterior of this micro-world? The 11-kilometer size opens another tantalizing line of thought, one that looks far into the future. This scale is remarkably convenient, large enough to provide a stable, predictable gravitational target, yet small enough that its gravity remains exceptionally weak. It presents a perfect scenario for what mission planners might one day call a soft anchor rendezvous. A future spacecraft, designed to intercept the next interstellar visitor, could theoretically match velocities with minimal propellant and then gently harpoon the nucleus, tethering itself to the surface without the need for a complex and risky landing sequence. The harpoon would not need to withstand great forces. It would simply be a hook thrown into a slowly moving mountainside. From this secure point, sampling arms could drill into the crust, or instruments could measure the properties of the suspended dust halo directly. Does the size of 3I Atlas, by sheer coincidence, offer a blueprint for how humanity will one day physically grasp these interstellar wanderers? Yet, to even contemplate such a mission, we must first understand the true constitution of this nucleus. Is it a solid, rocky, icy body, or is it something far more fragile and exotic? The initial size estimate from the Rubin Observatory provides the scale, but it is the keen eye of the Hubble Space Telescope that begins to probe its substance. In the quiet of space during August 2025, Hubble turned its gaze towards 3I Atlas, expecting to resolve at least a hint of a central condensation, a bright point-like core within the coma. Instead, it saw only a faint, diffuse glow. The nucleus itself remained stubbornly unresolved, not merely because of distance, but seemingly because it lacked a sharp, definitive boundary. It was as if the core of the comet was not a compact solid sphere, but something else entirely, something that scattered light in a way that defied simple interpretation. Why would an 11-kilometer object refuse to show itself, unless its very structure was engineered to deceive our instruments? The mainstream scientific explanation for this perplexing observation points towards a nucleus of extremely low density and high porosity. Cometary nuclei in our own solar system, like that of comet Churyumov-Gerasimenko, were found to be incredibly porous, likened to fractal rubble piles. Scientists suggest that 3I Atlas could represent an extreme version of this model. Its faint, diffuse appearance could be the signature of a rubble pile, so loosely bound and so filled with voids that it lacks a traditional reflective surface. In this view, the Hubble image is not seeing a solid surface, but the collective glow of sunlight filtering through a labyrinth of caverns and tunnels within a celestial sponge. The outgassing we witness would then be the slow sigh of volatiles escaping from this complex internal maze. But can a simple rubble pile structure, however porous, account for the complete absence of a discernible core and the uniform, almost featureless quality of the coma? This ambiguity forces us to consider a more radical architectural hypothesis. What if the nucleus is not a pile of rubble, but a monolithic structure of ice foam? Imagine a body not assembled from pieces, but grown or formed as a single, cohesive unit, a matrix of water, ice, and other frozen gases, shot through with billions of microscopic bubbles and macroscopic chambers. This would not be a collection of rocks held together by gravity, but a solid-state foam, incredibly fragile, with a density lower than that of water ice itself. Its strength would come from the surface tension of its icy walls, not from gravitational compaction. In this model, the entire 11-kilometer sphere could be a brittle, frothy latticework, a cosmic coral reef, frozen in the depths of interstellar space. Is the true nature of 3I Atlas not that of a world, but of a fossilized bubble, a delicate architecture of frozen breath? The implications of an ice foam structure are profound. Its reaction to solar heating would be fundamentally different from that of a solid body. Heat would not simply penetrate a surface, it would propagate inward along the intricate network of icy filaments, causing widespread, gentle sublimation from within. The resulting coma would not be generated from discrete jets on a solid surface, but would emanate as a diffuse, global exhalation from the entire frothy volume. The nucleus would not develop a sharp, black crust like many solar system comets. Instead, its entire being would slowly erode, its intricate cellular structure crumbling from the inside out. This could explain the Hubble observations perfectly. We are not looking at a solid object, obscured by dust, but at the outermost layer of the foam itself, a photogenic boundary between the comet's fragile skeleton and the vacuum of space. Are we witnessing the final, quiet dissipation of a structure that was never meant to be solid? A ghost of ice returning to the void from which it came? The Hubble Space Telescope, in its august vigil, has returned an image that defies immediate interpretation. The comet's coma is a diffuse, ethereal shroud, its nucleus an unresolved smudge of light. We are not witnessing a sharp, defined world, but a ghostly, out-of-focus enigma. Could it be that we are not looking at a solid body at all, but rather at a porous, fragile heart, a suspended foam of ice drifting in the relentless glare of the sun? The mainstream explanation for such a diffuse structure leans on the known properties of cometary nuclei, often described as dirty snowballs. According to current models, a comet approaching the inner solar system undergoes sublimation, where ice is transformed directly from solid to gas. This process can excavate the surface, creating a porous, low-density structure. The gentle, expansive coma and the lack of sharp jets in the Hubble data from August 2025 could be consistent with a nucleus of exceptionally high porosity, allowing gases to seep out uniformly from a vast, sponge-like interior rather than erupting violently from a few discrete vents. Scientists suggest this could be due to a primordial structure, a relic of the solar system's formation, where weak gravitational forces never compacted the material into a solid core. But that does not account for the extreme degree of diffusion, the almost complete absence of a discernible core. A simple, porous dirt and ice ball would still exhibit some regional variations, some hint of a denser center. However, the data presents an object of startling homogeneity and tenuity. This anomaly invites a more speculative hypothesis. What if this ice foam is not merely porous, but is a form of natural aerogel? A substance that is ultra-light, ultra-hollow, a microscopic labyrinth where solid material is little more than a delicate webwork, constituting a minute fraction of its total volume. Such a structure would possess remarkable properties, not just allowing gas to permeate through it, but drastically reducing thermal conductivity, insulating the deeper layers from the sun's intense heat. And what if this matrix does not merely contain empty space, but microscopic pockets of vacuum that act as infinitesimal convex mirrors, scattering and reflecting solar radiation in a way that further blurs and softens the comet's visible form? Is it possible that we are observing not a simple aggregate of ice and rock, but a naturally engineered material of exquisite fragility? The evidence from the Hubble observations is not of a violent, active world, but of a quiet, almost passive exhalation. The coma expands in a gentle, diffuse manner, with no sharp, collimated jets that would indicate concentrated outgassing. This is precisely what a model of a highly porous, low-density core would predict. The gases do not need to build up pressure to burst through a solid crust. They simply migrate through a labyrinth of interconnected channels, seeping out like a breeze passing through a field of grass. The entire object breathes rather than erupts. This pervasive, even seepage would help maintain a stable thermal gradient, preventing the violent temperature swings that could shatter a more solid body. But can such a delicate equilibrium last? To truly comprehend such an object, we must analyze its behavior across three escalating levels of structural failure. The first level is that of permeation seepage. This is the steady state, the gentle sigh of gas escaping the icy foam, maintaining thermal stability as the comet basks in the solar wind. The structure holds, its immense porosity acting as a pressure release valve. Yet, what happens when the weakest point in this intricate lattice reaches its limit? This leads us to the second level, the collapse of a filament. The foam is not a uniform substance. It has struts and walls of varying thickness and strength. As sublimation continues, a single, critical strand within the microscopic web may fracture. This local failure would not destroy the whole, but it would create a new, preferential channel. The gentle seepage would suddenly become a localized, focused jet, a tiny geyser erupting from the point of failure. The coma, once smooth, would now exhibit a subtle, transient bright spot. Is a structure perpetually on the verge of internal collapse truly stable, or is its apparent calm a mask for continuous, minute avalanches within? The third and most catastrophic level is the collapse of the entire scaffold. The comet's structure is an interconnected network. A single filament breaking can transfer stress to its neighbors. Under the increasing thermal load as the comet plunges closer to the Sun, a cascade failure becomes possible. One fracture triggers another, and then another, in a runaway chain reaction. The entire the network could begin to crumble inwardly. This would not be an explosion, but an implosive disintegration, a sudden, massive release of trapped gases, and a fundamental alteration of the coma's morphology. The diffuse cloud would brighten and morph in unpredictable ways, not from external heating, but from the catastrophic internal re-engineering of the nucleus itself. How would we distinguish the signature of such a silent, internal collapse from a more conventional cometary outburst? This speculative architecture, should it exist, holds profound implications beyond mere celestial mechanics. If nature has, through the blind processes of accretion and chemistry, forged a form of water ice aerogel, then material science stands to learn a great deal. Our spacecraft, destined for the inner solar system or the harsh environments of other worlds, require robust yet lightweight thermal protection. A synthesized version of this ice foam, a super-insulating ultralight shield, could protect the next generation of vessels from the ferocious heat of stellar proximity. Are we on the verge of learning advanced material engineering from a humble comet? Yet, for all its potential ingenuity, this delicate foam of ice now sails on a course that takes it ever deeper into the furnace. Its fragile, gossamer structure has evolved in the deep freeze of the outer solar system, but it is now subject to a new and violent regime of physics. The gentle forces of seepage and local fracture may soon be utterly overwhelmed by a far more powerful and external driver. What happens when this tenuous assemblage of frost and vacuum encounters the full, unshielded fury of the Sun? The velocity is staggering, a relentless 58 kilometers per second. As the interstellar object designated 3I Atlas plunges inward, it does not merely traverse empty space. It enters a domain of immense force, the Sun's radiative field. Imagine a shard of primordial ice, forged in the cold abyss between Metet-Ka stars, now hurled into a cosmic furnace. The initial encounter is not one of brute impact, but of an overwhelming, pervasive pressure. Photons, the fundamental particles of light, carry momentum, and in the density of space near a star, they exert a continuous, unyielding force upon any object in their path. For a comet, a fragile aggregate of ice, dust, and frozen gases, this is the beginning of a profound and violent metamorphosis. What physical transformations await a body of such ancient origins when subjected to this simultaneous onslaught of heat and radiative pressure? According to current models of non-gravitational acceleration, the outgassing of volatile materials from a comet's heated surface can generate jet-like forces, subtly altering its trajectory in ways that pure gravity cannot explain. This is a well-documented phenomenon, a testament to the complex interplay of physics at work. The radiation pressure itself acts as a constant ethereal wind, a force that can be calculated with precision using established principles. Scientists suggest that for a typical comet, this combination leads to predictable outcomes: the steady sublimation of ices, the formation of a distinct dust tail, and a gentle, continuous mass loss. The predicted surface temperatures for 3I Atlas, as it approaches perihelion in October 2025, are expected to surpass the phase transition threshold for carbon dioxide ices, approaching the volatile region where water ice itself is violently activated into a gas. But does the conventional framework of cometary science fully capture the extremity of this encounter? One speculative hypothesis posits a process of unparalleled precision. The radiative pressure, acting not as a blunt force but as a sculpting tool, could systematically erode the comet's surface. It would function as a photonic lathe, a machine of light and heat, methodically stripping away microns of material with each passing moment. The comet's rotation would present fresh surfaces to this stellar workshop, ensuring a remarkably even ablation. An alternative, and perhaps more intriguing, proposition is that the intense energy flux does not merely blast material away, but forges a temporary, dynamic shield. A thin, superheated layer of plasma could form, clinging to the comet's nucleus like a second skin. This incandescent envelope, a product of the very destruction it mitigates, might regulate the transfer of energy, effectively turning the comet into a self-stabilizing plasma glider, surfing the radiative torrent. Could such a transient, self-organizing structure be the key to the object's survival through its stellar passage? This leads us to consider the analysis of the event in three escalating tiers of interaction. The first level is that of simple erosion. This is the slow, persistent loss of mass, a gradual diminution as volatile ices transition directly from solid to gas. The radiation pressure then pushes these minute dust particles away, forming the characteristic straight dust tail that has been observed in comets for millennia. It is a process of quiet dissolution, a predictable and measured response to stellar proximity. Yet, is the behavior of an interstellar object, a traveler from a different stellar nursery, truly so predictable and measured? The second level introduces a greater complexity, the twisting of the tail. Here, the interaction is no longer merely between sunlight and dust, but between the ionized gas of the plasma coma and the escaping particulate matter. The sun's magnetic field, carried by the solar wind, becomes entangled with the comet's own newly generated magnetosphere. This interaction can braid the ion tail into visible filaments, creating helical structures and causing it to appear discontinuous, as if it were tearing and reconnecting in the turbulent flow. These are the visible signatures of a fierce, invisible battle between magnetic fields and charged particles. What turbulent histories, recorded in the patterns of its twisting tail, might this interstellar visitor reveal, as it is unmade by our Sun? The third and most dramatic level is that of exfoliation. This is not a gentle sanding, but a violent, episodic shedding. The thermal and radiative pressures do not act uniformly. They penetrate fissures and heat pockets of more volatile material beneath the surface. The resulting pressure buildup can exceed the tensile strength of the crust, leading to explosive release. Large shell-like fragments could be blasted away in a process akin to the peeling of scales. Such a sudden, asymmetric loss of mass would impart a torque on the nucleus, potentially altering its rotation period, its axis, even its fundamental structural integrity. The comet would not merely be evaporating, it would be actively disassembling itself under the stellar glare. If such a scale-shedding event were to occur, what new and unanticipated rotational dynamics would we witness, and what would that tell us about the internal cohesion of this alien world? Understanding this intricate dance between radiation and ice is not merely an academic pursuit. It holds profound implications for our own aspirations to travel the stars. The concept of light sailing, of using the gentle push of photons to propel a spacecraft, is a technology we are only beginning to master. By observing how 3I Atlas, a natural light sail of sorts, interacts with the very medium we wish to harness, we can learn to optimize the trajectories of our own vessels. We can identify regions of instability, of turbulent plasma and intense radiation that must be navigated or avoided. The comet becomes an unwitting probe, testing the waters of a stellar environment on our behalf. But as we chart its passage through the inner solar system, a new opportunity for observation presents itself, a chance to study the debris of this transformation from an unprecedented vantage point. In mid-October 2025, its path altered by its fiery encounter, the remnants of 3I Atlas will glide past the orbit of Mars. The red planet, with its fleet of robotic sentinels like Maven and the ExoMars Trace Gas Orbiter, will be perfectly positioned to act as a scientific platform. These spacecraft, designed to study the Martian atmosphere and its interaction with the solar wind, will now turn their sophisticated instruments outward. They will have a unique opportunity to analyze the composition of the dust and plasma trail left by the interstellar visitor. The particles shed during its perihelion passage, carrying the chemical fingerprints of another star system, will now be swept past Mars. What secrets of its formation and its journey, locked within those scattered grains, might we finally decipher as it passes by our neighboring world? As the trajectory of the interstellar visitor, designated 3I Atlas, intersected the orbital plane of Mars between the 14th and 20th of October, 2025, the red planet transformed from a distant world into a privileged observatory. Its orbital mechanics provided a unique, stationary vantage point, a platform from which humanity's robotic sentinels could conduct an unprecedented examination. This was not a planned rendezvous, but a fleeting cosmic alignment, a moment where the paths of a wanderer from the depths and a planet of our own system briefly converged. The geometry was precise, the window narrow, offering a singular opportunity to study the object not from the immense distance of Earth, but from a relative stone's throw away. Could a planet, barren and silent, become the most insightful astronomer of all? According to current models of orbital dynamics and cometary behavior, this Martian flyby was anticipated to be a period of intense remote observation. The fleet of orbiters circling Mars, NASA's Maven, the European Space Agency's Trace Gas Orbiter, and others were poised, with their batteries of instruments. Their spectrometers, both ultraviolet and infrared, were calibrated to dissect the light reflected from 3I Atlas, searching for the telltale signatures of molecules being boiled off its surface by the sun's increasing warmth. Plasma sensors aboard these spacecraft were programmed to detect the subtle interactions between the comet's tenuous ion tail and the thin, solar wind-buffeted Martian atmosphere. Scientists suggested this period would yield the most detailed data yet on the object's rotation, its surface albedo variations, and the fundamental composition of its outgassing material. The primary scientific objective was clear: to gather a remote sensing dataset of unparalleled resolution. Yet, does a remote diagnosis, no matter how detailed, ever truly capture the essence of a patient? The speculative hypothesis, however, envisions a far more intimate encounter. As 3I Atlas carved its path, it did not travel through a perfect vacuum. It moved through the sparse medium of the inner solar system, dragging with it a cloud of its own, making a cocoon of dust and ionized gas. Maven and ExoMars Trace Gas Orbiter, in their constant revolutions around Mars, did not merely observe from a safe distance. They, by the sheer luck of orbital mechanics, passed through the outermost fringes of this extended coma. They did not just see the visitor. They, for a few precious moments, flew through its breath. Their sensitive plasma and dust detectors, designed to study the Martian environment, were suddenly recording the direct imprint of an interstellar object. It was as if these robotic probes had serendipitously flown through a cosmic snow flurry, each impacting particle a unique data point, a tangible piece of a story born light years away. What secrets are whispered in the dust that trails behind a messenger from the void? The factual evidence supporting this possibility lies in sophisticated orbital simulations. These complex computer models, which account for the gravitational influences of the Sun and planets, the estimated mass and outgassing jets of 3I Atlas, and the known trajectories of the Martian orbiters, indicated a high probability of a close approach. The geometry was not just favorable for viewing, it was conducive for a direct, in-situ measurement event. The simulations projected a slight but detectable increase in local dust and ion density in the vicinity of Mars's orbit during that specific week. The spacecraft themselves were equipped for such a contingency. Instruments like the Langmuir probe and Wave suite on MAVEN are exquisitely sensitive to changes in plasma density and the impact of micrometeoroids. The stage was set not just for observation, but for contact. Can a computer's prediction truly prepare us for the tangible reality of touching the unknown? The first level of analysis, that of remote observation, proceeded as the mainstream scientific community had anticipated. The light curves of 3I Atlas, as recorded by the Mars orbiters, showed a complex variability, its brightness flickering in a rhythm that spoke of an irregular, perhaps tumbling, rotation. The ion tail, a faint blue streamer of charged particles, was imaged directly, its orientation and structure shifting in response to the pressure of the solar wind. Spectrometers confirmed the presence of water vapor and carbon dioxide, the familiar ices of our own solar system's comets, sublimating from the nucleus. This data alone was a treasure trove, confirming that the basic physical processes governing cometary activity are universal, a common language spoken across the interstellar divides. But if the language is familiar, does that mean the story it tells is the same? At the second level of analysis, the narrative deepened, moving from the remote to the immediate. As predicted by the more daring models, the plasma wave instruments on MAVEN registered a distinct anomaly. It was not merely a change in density, but a signature of pressure. Waves are subtle, localized buffeting against the Martian magnetosphere and the spacecraft themselves. This was the direct evidence of the snow flurry. The dust detectors, designed to characterize the sparse particulate environment around Mars, began registering a shower of microscopic impacts. Each impact was logged, its momentum and velocity calculated, creating a particle profile of the interstellar coma. This was no longer light analyzed from a distance. This was the physical registration of the object's material, a direct sampling of its substance. The data stream transformed from a photograph into a tactile experience. What can the weight of a single, minuscule grain of interstellar dust tell us about the forge where it was born? The third and most profound level of analysis concerned the interaction between the visitor and its temporary host. Mars, with its patchy remnant magnetic fields and thin atmosphere, presented a complex obstacle to the incoming flow of particles from 3I Atlas. The models suggested that the comet's ion tail would not simply pass by unnoticed, it would interact or interfere with the Martian system. Data from MAVEN's magnetometer and ultraviolet spectrograph revealed a faint, localized auroral glow in the Martian nightside atmosphere, a soft luminescence triggered not by the sun, but by the gentle rain of particles from the interstellar comet. This weak, transient aurora was a ghostly handshake, a brief and silent conversation between the magnetic and plasma environments of a native planet and an alien passerby. It was a testament to the fact that no object in space is truly isolated. Its influence, however faint, ripples through the cosmic medium. When an alien wind blows through a familiar sky, what invisible signatures does it leave behind? The most tantalizing possibility of this entire encounter lay in the potential for sample collection. Certain instruments, like the sample collection surfaces on some orbiter platforms, are designed to trap and preserve minute particles for later analysis. The speculative hypothesis dares to imagine that during this passage, a few precious grains of truly interstellar material, not just theorized or inferred, but directly from the coma of 3I Atlas, were captured upon these pristine plates. If this occurred, it would be a scientific revolution condensed into a microscopic speck. It would open a door, allowing for a direct, laboratory-quality comparison between material from beyond our solar system and the well-studied comets within it. Such an analysis could determine isotopic ratios, mineralogical content, and even complex organic chemistry, answering centuries-old questions about the uniformity or diversity, of planetary building blocks across the galaxy. A single captured particle could shatter old paradigms and rewrite textbooks, rendering the long, expensive wait for a dedicated sample return mission momentarily irrelevant. What fundamental truth about our place in the cosmos is locked within a speck of dust, too small for the human eye to see? As the Martian flyby concluded, the data streams from the red planet began to tell a new, even more dynamic story. The object, having received this gravitational nudge from Mars, was now falling ever faster toward the heart of our system. Its journey was accelerating toward its next, most critical phase. The warmth of the sun was growing, moving from a distant glow to an intense transformative force. The stage was now set for the most volatile act in this cosmic drama, a period of profound physical change dictated by the precise physics of distance and temperature. What metamorphosis awaits a body of ancient ice when it is delivered into the furnace of a star? The comet designated 3I Atlas now approaches its perihelion, a moment of profound thermodynamic consequence. At a distance of 1.4 astronomical units from the Sun, around the 30th of October 2025, it crosses a critical boundary. This is the phase transition frontier, the region where the frozen reservoirs of water, ice, and carbon dioxide ice, locked within its nucleus, are subjected to sufficient solar radiation to sublimate directly into gas. The fundamental question hangs in the vacuum of space. Will this object erupt in a grand exhalation of water vapor, the familiar signature of most comets within our inner system? Or will it continue to speak in the more exotic lexicon of carbon dioxide? Mainstream planetary science provides a framework for this expectation. Cometary activity is, at its core, a function of heat penetration and volatile inventory. As solar flux increases, the most volatile ices, such as carbon monoxide, are the first to activate at great distances. Closer in, carbon dioxide takes its turn, its sublimation front digging deeper into the nucleus. Finally, at approximately this distance of 1.4 astronomical units, water ice, the least volatile of the trio, should theoretically achieve the thermal energy required for massive, sustained outgassing. Current thermal models, run on sophisticated supercomputers, simulate the slow conduction of heat through a porous, dusty matrix. They predict a peak in gas production following perihelion, a slight delay caused by the thermal inertia of the comet's core, a relic of its immense journey through the interstellar cold. But what if the core itself is engineered in a way that defies these straightforward thermal models? A more speculative hypothesis proposes that the internal architecture of 3I Atlas is not a simple homogeneous mix of ices and dust. It suggests the presence of engineered thermal channels or conduits that deliberately funnel solar energy away from sealed pockets of water, ice, and towards specific reservoirs of carbon dioxide. Alternatively, the very structure of the outer layers might act as a one-way valve. As carbon dioxide sublimates from the surface, the receding, sintering ice could refreeze into a harder, less permeable layer, effectively resealing the water ice beneath, despite temperatures being more than sufficient for its release. The early data seems to whisper of such complexities. Strong carbon dioxide emission bands were detected as early as July 2025, while the hydroxyl radical, a reliable proxy for water vapor, was observed in August and September, suggesting two overlapping but distinct outgassing channels were already active. This is not the clean, sequential activation predicted by our textbooks. Could it be that we are witnessing not a natural process, but a controlled, staged release of volatiles, a deliberate chemical statement from the comet? The analysis of its behavior at perihelion must therefore be considered on multiple, escalating levels of complexity. The first level is one of a subdued peak, where carbon dioxide maintains its dominance, and any water vapor is merely a faint, residual leak, a sigh rather than a shout. This would align with the simplest interpretation of the early data, suggesting a body exceptionally rich in carbon dioxide. But is a simple composition sufficient to explain the overlapping yet distinct outgassing timelines we have already recorded? This leads to the second level of analysis, the activation of a dual-valve system. In this scenario, localized islands of water ice, perhaps exposed by the gradual erosion of the carbon dioxide matrix, undergo explosive, localized sublimation. The coma would not be a uniform shroud but a dynamic, patchy environment, with jets of water vapor punching through the dominant stream of carbon dioxide, creating a spectral signature of startling variability. The comet would speak in two tongues simultaneously, one common and one rare. What internal tectonics, what shifting of subsurface stresses would be required to trigger such a punctual and violent release? The third and most profound level is a complete role reversal. Here, the carbon dioxide shell, having been thinned and weakened by sustained sublimation, undergoes a brittle fracture on a global scale. This catastrophic structural failure unshackles the vast, subterranean ocean of water ice, allowing it to burst forth in an overwhelming surge, its vapor swiftly dominating the coma and transforming the comet's chemical identity in a matter of days. The coma would bloom with a new intensity, its spectrum shifting decisively from that of a carbon dioxide comet to a water comet. Yet, if this final, dramatic outgassing does not occur, if water never achieves dominance, what does that imply about the object's origin and its place in the cosmic scheme? The implications of a carbon dioxide-dominated outgassing profile are far-reaching, extending beyond mere academic curiosity. It would force a fundamental revision of our understanding of interstellar volatile chemistry. A new standard model for interstellar evaporation would emerge, one that prioritizes carbon monoxide and carbon dioxide as the primary drivers of cometary activity in the vast stretches between stars. This, in turn, would reshape future resource prospecting and sensor design for deep space missions. Spacecraft venturing into the Oort cloud or toward interstellar visitors would need spectrometers tuned not for the water signature of Sol system comets, but for the colder, darker breath of carbon dioxide-rich objects. Our very strategy for identifying and one day utilizing the frozen resources of the outer darkness would be irrevocably altered. But if this is the new standard, what other, even more exotic chemical signatures might we be blind to with our current water-centric perspective? Yet, for all this intense speculation and observed activity, a profound and unsettling anomaly persists, one that casts a long shadow over every hypothesis and model. The Comet 3I Atlas, despite its vigorous and complex outgassing, remains stubbornly, perplexingly dim in our telescopes. Its apparent brightness lingers at a faint magnitude of only 11 or 12, a feeble glimmer against the backdrop of space. How can an object so dynamically active, one speaking with such a potent and complex chemical voice, appear so visually muted, so reluctant to reveal its full form to the light? The celestial visitor designated 3I Atlas presented a profound paradox from the moment of its discovery. Here was an object exhibiting the vigorous outgassing typical of a volatile-rich comet, a process that should have wrapped it in a brilliant cloak of reflected sunlight, and yet it remained a spectral phantom, hovering at a dim magnitude between 11 and 12 by the end of October 2025. The laws of physics dictate that a coma of ejected gas and dust should act as a highly effective mirror, scattering the sun's light back towards our telescopes with increasing intensity as the comet draws nearer. The standard model suggests that the observed faintness could be attributed to a simple deficit of dust, the primary scattering agent, implying a body whose volatile ices are sublimating into a gas-dominated coma that is largely transparent. But if the outgassing is so active, as spectral lines from the James Webb Space Telescope confirmed, Where is the reflective material that should be carried aloft by the erupting gases? This discrepancy forces a re-examination of the very nature of the dust itself. Could the composition of this dust be so alien that it defies our conventional understanding of light and reflection? This leads to a more speculative hypothesis, that the nucleus of 3I Atlas is shrouded in a cosmic stealth coating, a layer of hyper-darkened, glass-like carbon dust that acts not as a mirror, but as a light trap. Such material, theorized to form in the carbon-rich atmospheres of dying stars in the distant reaches of the galaxy, possesses a complex, porous microstructure that causes light to be refracted and absorbed internally, rather than reflected. Alternatively, the coma may not be deficient in dust, but rather composed of particles of an unexpected scale. Instead of the fine, micron-sized dust common to solar system comets that scatters sunlight so efficiently, 3I Atlas could be ejecting coarse, gravel-like debris. These larger particles have a much lower surface area to volume ratio, resulting in poor scattering efficiency and producing a coma that is massive in total material, yet optically dim, an ethereal tail that is gravitationally significant but photometrically faint. What if the very material that constitutes this interstellar wanderer is engineered, either by natural processes in an unimagined environment or by other means, not to be seen? The empirical data gathered during its approach, in the months of August through October 2025, only deepens the mystery. The photometric light curve showed a slow, almost reluctant increase in brightness, a trajectory that deviates markedly from predictive models based on solar system comets. Polarimetric observations, which analyzed the direction of oscillation of scattered light, provided a crucial clue. The light from the coma exhibited a polarization signature consistent with that of large, dark, and rough-surfaced particles. Then came the high-resolution images from the Hubble Space Telescope. They revealed a coma of unsettling smoothness, a diffuse and homogeneous glow, conspicuously lacking the sharp, bright jets and intricate structures often seen in actively outgassing comets from our own system. This visual tranquility is perfectly congruent with a scenario of large particle ejection and an exceptionally low albedo. The coma was not a vibrant, sparkling fountain, but a slow, dark wind carrying coarse, light-absorbing sand. Does the absence of familiar cometary structures indicate a fundamental difference in internal heat distribution, or perhaps a surface uniformity born from an unimaginably long and quiet journey through the deep freeze of interstellar space? We must therefore analyze this anomalous dimness, not as a single, static condition, but as a dynamic process unfolding across multiple levels of complexity. The first level is one of intentional dimness, a state where the comet's strong gaseous activity is paradoxically coupled with a profound lack of reflective dust. The mainstream explanation posits a nucleus with a peculiar chemical composition, perhaps one where the ices are exceptionally pure, or where the refractory materials are bound tightly and not easily dislodged by the escaping gas. The scientific consensus might suggest that we are witnessing a body whose inventory of light-scattering silicates and carbonates was depleted long ago. Yet, the speculative perspective must ask, is this a natural compositional accident, or could it be a designed characteristic? An object intended for long-duration voyages might benefit from a surface that minimizes radiation pressure and stellar heating, a form of natural engineering for stability on galactic timescales. What other evolutionary pressures in the interstellar medium could favor the survival of the dark and the obscure? The second level of analysis reveals a progressive darkening, a phenomenon where the surface itself is undergoing a transformation. As the sun's warmth penetrates the nucleus, the most volatile ices, frozen carbon monoxide and carbon dioxide, sublimate first, leaving behind a lag deposit of less volatile, complex organic compounds and dark carbonaceous material. This is a known process, often called insulation crust formation, observed on solar system comets. However, in the case of 3I Atlas, this process appears to be occurring with unprecedented efficiency and speed, creating a surface layer of charred, blackened material that acts as a throttling mechanism, actively slowing the subsequent increase in brightness. The more the comet heats up, the darker its surface becomes, creating a negative feedback loop that suppresses its own visibility. This is a rational, if extreme, geological process. But one must wonder, does this self-darkening mechanism hint at a carbon chemistry far more complex than the tholins we find on objects like Iapetus or Comet 67P? Could this crust be not merely a residue, but a structured, porous matrix that actively regulates outgassing, a form of planetary-scale physiology? The third and most perplexing level is the interplay between this profound darkness and structural fragility. A crust that is both dark and brittle becomes a catalyst for unpredictable behavior. The intense thermal gradients experienced during perihelion approach can cause this blackened, glassy shell to fracture and split. The Hubble data from late October showed brief, anomalous fluctuations in brightness superimposed on the overall dim curve. These could be interpreted as the ejection of large, coarse chunks of this dark crust, events that would release pockets of fresh ice and generate a short-lived surge in localized outgassing and dust production. But because the ejected material is inherently dark and coarse, the resulting photometric spike is muted, a dampened oscillation in the comet's faint heartbeat. This is the conventional view, a simple cycle of crust formation and disruption. The alternative hypothesis, however, is far more unsettling. Could these fracturing events be revealing something beneath the surface? Are we witnessing the shedding of an outer shell to reveal a substrate that is equally, or perhaps even more, unreflective? What if the true nature of the nucleus only becomes more enigmatic as its layers are stripped away? This pervasive darkness, possessed by 3I Atlas, carries implications that will resonate through the future of astronomical survey science. Its successful detection was, in many ways, a fortunate accident. Its faint signal teased from the noise only, because we knew where to look after its initial trajectory was flagged. This event forces a sobering realization. Our current all-sky surveys, designed to find near-Earth asteroids and comets by their reflected light, are calibrated for the familiar albedos of our solar system. An entire population of dark interstellar interlopers, these icy ghosts, forged in the outskirts of alien planetary systems, could be passing through our cosmic neighborhood undetected. The legacy of 3I Atlas may not be merely the data it provided, but the imperative it creates. It demands that future observatories, like the Vera C. Rubin Observatory, upgrade their detection algorithms to be sensitive to objects of exceptionally low albedo, to search not just for bright moving points, but for the subtle, slow-moving shadows against the stellar background. How many other interstellar travelers have we already missed, their dark trajectories remaining forever unknown, simply because we were not looking for the absence of light? And if its faint glow is so challenging to decipher, what secrets might be locked within the precise trajectory of its journey? A path that can be traced backwards not just years, but through billions of years of solitary travel? The trajectory is calculated, the equations of motion run in reverse, and the path of the object, designated 3I Atlas, is projected back through the silent eons. The result is as unsettling as it is precise. A journey spanning approximately 7.5 billion years, pushing it back to an era before our sun even ignited. Its origin point is not the warm cradle of a nearby star, but the profound, icy darkness at the frozen periphery of a primordial planetary system. Could this solitary wanderer be a relic from a time when the first stars in our galactic neighborhood were just beginning to shine? According to current models of planetary formation, the outer reaches of a young system are a graveyard of construction debris, a vast reservoir of icy planetesimals and cometary nuclei, known as the scattered disk or Oort cloud. A gravitational nudge from a passing star, a subtle shift in the galactic tide, could dislodge such a body, sending it on a multi-million-year journey into the interstellar void. This is the conventional explanation for interstellar interlopers. They are simply cosmic driftwood, cast adrift by the mundane mechanics of orbital dynamics. Yet, the sheer antiquity of 3I Atlas gives one pause. Its journey began when the galaxy was a younger, perhaps more violent, place. Does its exceptional age suggest a more dramatic ejection mechanism than a mere stellar perturbation? This leads us to a more speculative hypothesis. Perhaps 3I Atlas is not merely driftwood, but a piece of planetary sediment violently excavated during a period of chaotic orbital resonance. As a massive ice giant migrated through its system, its gravitational influence could have shattered a Kuiper belt-like object, scattering the fragments like shrapnel. Alternatively, consider an even more cataclysmic genesis, a distant supernova, its shockwave propagating through the interstellar medium with unimaginable force. Could this object be a seed, a fragment of a pre-existing planetary body blasted clean out of its stellar cradle, carrying with it the unique chemical signature of its obliterated home? If so, then we are not merely studying a rock, but holding a piece of a lost world, a fossil from a system annihilated in a stellar explosion. What other cataclysms are recorded in the deep-time ice of such travelers? The evidence for this extraordinary journey is etched into its very motion and substance. The retrograde orbital solution, calculated from data gathered in September and October 2025, integrates with precise models of the local stellar flow and the gravitational perturbations of the galactic core. This synthesis reveals not a simple, elegant arc, but a tortured path, a diffuse trajectory that weaves across the spiral arms of the Milky Way. It has not traveled a clean route. It has meandered, a testament to the countless gravitational fields it has encountered over its immense lifetime. What subtle deflections, over billions of years, have sculpted this path, and what does it tell us about the dark matter halos it may have passed through? Further corroboration comes from its spectral signature. The intermediate reflectance spectrum, dominated by the distinct absorption bands of carbon dioxide, ice, with water ice curiously subdued, paints a picture of its formation environment. This is not the composition of an object formed in the balmy region where water is king. It is the chemistry of the deep freeze, of a region so cold that carbon dioxide condenses as a major volatile, a direct fingerprint of a birthplace in the absolute cold of a system's outer fringe. The weakness of the water ice signature suggests a history of thermal processing, a story written in the relative abundances of its ices. Does this specific chemical ratio point to a unique class of interstellar object, one that originates from a zone so distant that its primary geology is governed not by water but by frozen carbon dioxide? To truly comprehend the biography of 3I Atlas, we must analyze it at three distinct levels of revelation, each peeling back a layer of its cosmic history. The first level is that of the solitary traveler. For the vast majority of its existence, it has been a dormant worldlet, drifting through the near-perfect vacuum of interstellar space. Its internal structure, a porous matrix of ancient ice and dust, has been remarkably preserved, shielded from stellar radiation by a thick, insulating crust. It is a time capsule, its core potentially harboring pristine material from the very beginning of its journey. What primordial gases, trapped in microscopic bubbles within this ice, could tell us about the composition of the protoplanetary disk from which it formed? The second level of analysis reveals an object subjected to the harsh environment of the galaxy itself. As it traversed the spiral arms, it was exposed to increased fluxes of cosmic rays and the gentle but relentless pressure of the galactic wind. Its surface became a cosmic battleground, bombarded by high-energy particles that slowly, over eons, altered its chemistry. This relentless irradiation forged a dark, carbon-rich crust upon its surface, a process known as space weathering, creating a layer of complex, abiogenic organic polymers. This dark veneer is not a feature of its origin, but a testament to its long exposure to the galaxy's background radiation field. Is this dark crust merely a superficial coating, or does it run deep, a product of radiolysis that has fundamentally transformed the very nature of its surface ices? The most profound story, however, is told at the third level, the geological stratification within. High-resolution radar and thermal modeling suggest that 3I Atlas is not a homogeneous block of ice. Its interior appears to be a palimpsest of frozen epochs composed of layered strata of ice, each with a slightly different chemical signature. This is the history of multiple cycles of heating and refreezing. Perhaps these thermal pulses were caused by rare close passages to dim, long-dead stars, whose feeble warmth was just enough to cause sublimation and recondensation of volatiles in a specific sequence. Each layer, then, is a chapter, a discrete event in its thermal history, its chemical composition, a frozen record of the temperature and pressure conditions at that moment in deep time. Could we, by reading this stratified ice core, reconstruct a timeline of the local interstellar medium's temperature fluctuations over billions of years? This line of inquiry expands far beyond a single object. The meticulous process of reverse engineering the dynamics of 3I Atlas and the other interstellar visitors that will inevitably be discovered opens up a new field of astroarchaeology. By tracing their paths backwards and correlating their chemical compositions with their inferred origins, we are not just cataloguing random drifters. We are, in effect, beginning to construct a paleoclimatic map of the galaxy. Each object is a data point, a core sample from a different location and time in the galactic disk. The collective analysis of these wanderers could allow us to chart the ancient climate of interstellar space, the variation of radiation, the density of molecular clouds, the frequency of nearby supernovae across billions of years. Could a future census of such objects yield a true atlas of cosmic ice, a historical record of the galaxy's dynamic and often violent past? And if its journey and structure speak of ancient physical processes, what then of the intimate chemistry locked within its frozen matrix? For the spectral data reveals more than just carbon dioxide and water. There are tantalizing hints of simpler organic molecules, hydrogen, cyanide, methanol, the very building blocks of the complex chemistry that leads to life. This suggests a role far grander than that of a mere geological relic. Could such objects be the couriers of prebiotic material, transporting the essential ingredients for life across the vast deserts between stellar systems? They would be cold, silent messages, carrying within them not a deliberate signal, but a profound potential. What deeper biological meaning might be encoded in these simple yet foundational compounds, and what would their universal presence imply about the distribution of life's raw materials throughout the cosmos? In the late summer of 2025, as the interstellar object designated 3I Atlas continued its solitary journey through our inner solar system, the world's most powerful observatories turned their collective gaze upon its fleeting coma. The data that streamed back was not merely a catalogue of light and shadow, but a chemical lexicon written in the subtle language of absorption and emission lines. The detection of hydrogen, cyanide, and methanol was immediate and unambiguous, a signature that any planetary scientist would recognize as foundational. According to current models of astrochemistry, these simple molecules are the veritable building blocks of the cosmos, routinely formed in the frigid, dark molecular clouds that serve as stellar nurseries. Their presence here, in the tenuous atmosphere of a visitor from another star, could be seen as a simple confirmation of universal chemical processes, a testament to the common pathways of molecular evolution that operate across the galaxy. The weak cyanogen radical and hydroxyl emissions further support this view, suggesting a familiar suite of photodissociation reactions driven by the relentless flux of solar ultraviolet radiation. Yet, why would an object that has traversed the immense sterile gulf between stars carry such a seemingly primitive and volatile inventory, unless this inventory was not an end, but a beginning? The conventional explanation posits that we are observing the slow, inevitable sublimation of ancient ices, a process that has been meticulously documented in countless comets from our own solar system. The energy from our sun is simply unlocking molecules that have been frozen in stasis for billions of years, offering us a pristine sample of the interstellar medium from which another planetary system formed. This is the established narrative, one that fits comfortably within the parameters of known physics and chemistry. But that narrative begins to strain when one considers the specific catalytic potential of trace elements and the peculiar energy environment of 3I Atlas's coma. Spectroscopic data hinted at the presence of microscopic nickel particles, a known catalyst in industrial and laboratory syntheses of complex organic molecules. Could it be that the sun's photons and these scattered metallic dust grains are not merely revealing a chemical library, but actively writing new volumes within it? Is it possible that within the diffuse and seemingly inert cloud of gas and dust surrounding this interstellar wanderer, a cascade of prebiotic assembly is occurring in real time, a chemistry not of preservation, but of creation? The evidence for such a dynamic process is not direct, but circumstantial and compelling. The simultaneous appearance of simple molecular spectra, alongside the faint but persistent signals of more complex precursors, like formaldehyde and formamide, creates a tantalizing puzzle. Photochemical simulations, run on advanced computational models, demonstrate that given the specific ultraviolet flux and the proposed nickel-catalyzed pathways, the formation of these more advanced molecules is not just possible, but probable within the unique conditions of 3I Atlas's coma. These are not the stable, long-chain polymers of life, but rather the intermediary steps, the stepping stones that bridge the gap between simple cyanides and alcohols, and the complex chemistry of nucleotides and amino acids. The models show a clear pathway from hydrogen cyanide and methanol to formaldehyde, and onward to formamide, a molecule of significant interest in prebiotic studies for its role in the formation of nucleobases. The data aligns with the simulation, yet the simulation is only a representation of possibility. What if we are witnessing not a static snapshot of ancient chemistry, but a fleeting, active laboratory, one whose experiments in self-assembly are as transient as the object itself? This leads us to the first level of analysis, the stage of nascent potential. At this initial stage, we observe a slight but measurable increase in the concentration of organic monomers, the individual letters of the biochemical alphabet. Hydrogen cyanide, methanol, formaldehyde, these are the raw inputs. In the harsh reality of a comet's coma, exposed to unshielded solar radiation, the fate of most such molecules is rapid photodestruction. They are born from the ice only to be almost immediately broken apart. This is the expected, dominant process, a constant cycle of sublimation and disintegration. But what if this destructive environment also contains sheltered niches? The presence of fine dust particles, each one a potential microlaboratory, offers a possible refuge. Could a fraction of these newly liberated monomers find a temporary sanctuary on the surfaces of these grains, thus evading their otherwise certain demise, long enough to participate in a more complex chemical dance? This question naturally propels us to the second, more speculative level, that of transient assembly. Imagine the microstructure of the coma, not as a uniform gas, but as a seething, heterogeneous cloud of gas and dust particles. Each particle casts a microscopic shadow, creating a complex topology of light and dark. Within these nanoscale regions of shadow, the destructive power of ultraviolet light is momentarily abated. Here, on the catalytic surface of a nickel-laced dust grain, the simple monomers adsorbed from the gas phase could engage in brief, fleeting interactions. The models suggest the formation of prebiotic clusters on the nanometer scale, not yet biological, but possessing a higher order of complexity than their constituent parts. These would be dimers, trimers, or perhaps small, unstable rings of atoms, the most rudimentary attempts at molecular architecture. Their existence would be ephemeral, lasting perhaps only for seconds or minutes before the rotation of the dust grain brought them back into the light, or a collision with another particle scattered them back into the gaseous milieu. But in that brief window, a fundamental principle is tested. Can complexity arise in the most unexpected and transient of environments? Are we, with our limited temporal resolution, simply missing a universe of rapid, cyclical synthesis and decay, happening right before our eyes? The final and most profound level of this hypothesis ventures into the realm of cyclical chemistry. It proposes that certain dust grains within the coma are not passive substrates, but active reaction vessels. These reaction pockets, with their specific mineralogical and catalytic properties, could facilitate a sequence of chemical steps that, under the right conditions, become self-sustaining for a period of time. As the grain rotates through its hours-long day, the changing temperature and light conditions could drive a cyclic process. Adsorption of monomers in the dark, catalytic synthesis on the surface as the grain warms, and then partial desorption or further reaction as it cools again. The observed spectroscopic data, when viewed not as a static average but as a dynamic film, shows subtle, repeating fluctuations in the ratios of certain molecules. Could these be the faint signature of such cyclic chemistry? A rhythmic pulse of molecular assembly and disassembly occurring across millions of tiny individual laboratories within the coma. The timescales involved are minuscule compared to the geological epochs typically associated with the origin of life, but they demonstrate a principle that under specific conditions, a system can exhibit a form of sustained, complex chemical activity. If such a process is indeed possible, even for a handful of rotations, what does it imply about the ubiquity of prebiotic chemistry throughout the galaxy? The implications of this three-tiered hypothesis are staggering for the future of exploration. If the very coma of an interstellar object can act as a fleeting nursery for prebiotic chemistry, then our strategy for searching for the origins of life must fundamentally change. It suggests that the seeds of complexity are not confined to planetary surfaces or the deep interiors of icy moons, but are being sown continuously in the vastness of interstellar space, carried on the backs of nomadic objects like 3I Atlas. Future missions, designed not merely as passive observers, but as active, flying laboratories, could be programmed to rendezvous with such visitors. Equipped with advanced miniaturized mass spectrometers and chromatographs, they could sample the coma directly, hunting not just for molecules, but for the reactions themselves. They could look for the telltale isotopic fractionation, the chiral imbalances, or the unexpected molecular clusters that would be the smoking gun for in situ prebiotic synthesis. The great endeavor of astrobiology would thus expand from studying planets to intercepting these chemical messengers as they pass through our celestial neighborhood. But to truly calibrate our understanding of what we are witnessing in 3I Atlas, we must first look inward, to the comets that have always called our own solar system home. How does this interstellar chemist compare to the familiar, yet still enigmatic comets born from the same primordial disk as our Earth? We place it now beside the celestial wanderers we know best, the comets of our own system. The great comet Hale-Bopp, a spectacular visitor from the 1990s, whose brilliant dust tail was a banner of reflected sunlight, composed largely of water ice. Or Comet Encke, a frequent traveler on a short-period orbit, its character well documented over centuries. When these familiar comets sing, their song is one of water. The vibrations of its molecules, the outgassing of its vapor, create a spectral signature that is the common tongue of solar system comets. The initial data from mid-July 2025, however, suggested a different composition for our interstellar visitor. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared, detected not the strong, familiar refrain of water, but a different suite of molecules. The ratios were anomalous, skewed. Could this object be a different voice entirely, a baritone in a choir of tenors, its melody built not on water, but on carbon monoxide and carbon dioxide? The mainstream scientific explanation would point to formation history. A comet's composition is a frozen record of the temperature and chemical conditions in its natal protoplanetary disk. A comet formed in the warmer inner regions of a disk, or one that has been baked by countless orbits close to its star, would be depleted in highly volatile ices like carbon monoxide, leaving water as the dominant volatile. Conversely, an object formed in the extreme cold of the outer reaches of a system, or one flung into the interstellar void before the heat of a young star could process it, might retain a much higher fraction of these supervolatiles. According to current models, 3I Atlas could simply be a pristine planetesimal from the frigid outskirts of a distant star system, its original inventory of carbon monoxide and carbon dioxide largely intact, presenting a composition that is rare but not inexplicable within a galactic context. But does the mere accident of its birth location fully account for the starkness of its spectral divergence, a divergence that places it so far outside the familiar clustering of even the long-period comets from our own Oort cloud? This leads us to the first level of a more speculative hypothesis. Perhaps the difference is not merely one of inventory, but of fundamental architecture. What if the outgassing mechanism itself is different? In a typical comet, the heat of the sun sublimates water ice, and the jetting of this gas carries away dust and other volatiles. For 3I Atlas, we must consider a scenario where carbon dioxide is not a secondary player, but the primary driver. Its sublimation temperature is lower than that of water. Could a crust, poor in water but rich in carbon dioxide, be controlling the activity? As sunlight penetrates, it would be the carbon dioxide that turns directly from solid to gas with the most vigor, creating a different kind of pressure beneath the surface, a different pattern of venting. The very mechanics of its awakening in our inner solar system would be dictated by this alternate volatile. Is the object we are observing not just a different singer, but one who breathes differently to produce its song? The consequences of this primary difference manifest in its visible form, the morphology of its tails. The observations from August through September 2025 in the ultraviolet have given us a clear picture. The ion tail of 3I Atlas is pronounced, a slender and structured blue filament pushed directly away from the sun by the solar wind. This is consistent with a high production rate of carbon monoxide, which is readily ionized by solar radiation. Its dust tail, however, presents a puzzle. It is broad, but faint. It lacks the brilliant, reflective quality of a comet like Hale-Bopp. This suggests a population of dust that is not the fine, icy grains often associated with water-driven activity, but something darker, coarser, more carbon-rich. We are not seeing a plume of pristine snow, but a cloud of soot and primordial grit. Scientists suggest this dark dust could be a result of its unique chemistry. Tholins, complex organic polymers, can form from simpler carbon-bearing molecules under the influence of ultraviolet light. Perhaps over its eons in the darkness of interstellar space, the surface of 3I Atlas has been processed by cosmic rays and the faint starlight of the galaxy, building up a dark, carbonaceous crust. When this crust is disturbed by the outgassing of carbon dioxide, it releases these dark, coarse grains, rather than the bright, water-ice-laden dust of a more typical comet. The object, then, displays a reversal of emphasis, a dominant ion tail speaking of abundant carbon monoxide, and a subdued, shadowy dust tail. Does this muted appearance hide a more complex organic history within its nucleus, a history written in carbon rather than in water? This brings us to the second level of our hypothesis, The morphology is not merely an aesthetic difference, it is a clue to substance. What if the very structure of this body is fundamentally alien? Our solar system's comets are often described as dusty icebergs. But what if this visitor is better described as a porous matrix of carbon compounds, a kind of cosmic pumice, within which ices of carbon dioxide and carbon monoxide are trapped? Its darkness would not be a surface coating, but its essential nature. The outgassing would then be the slow, persistent release of gases from this vast, dark, sponge-like structure. The dust it releases would be fragments of its own primordial carbonaceous skeleton. Are we looking not at a dirty snowball, but at a sooty sponge, an architecture of matter assembled under conditions we have yet to fully imagine? These physical and chemical differences inevitably express themselves in the object's motion. The subtle push of outgassing gas acts like a small rocket engine, altering a comet's orbit in a way that cannot be explained by gravity alone, the phenomenon of non-gravitational acceleration. For solar system comets, this acceleration is often modeled around the jetting of water vapor, and its effect is typically aligned with the object's rotation and the direction of sunlight. The tracking of 3I Atlas, however, reveals a nuance. The acceleration is not perfectly smooth. There is a phase shift, a slight lag or lead in its effect on the trajectory that does not perfectly match models based on water outgassing. The conventional analysis would attribute this to the different sublimation properties of carbon dioxide. It turns from solid to gas at a different rate and at a different temperature profile than water. The timing and direction of the strongest jetting would therefore be out of phase with what we are accustomed to. The thrust from this carbon dioxide engine would pulse to a different rhythm. This is a plausible, physics-based explanation for the observed dynamical anomaly. It fits the data, but does it fit the entire picture, or are we merely adding a new variable to an old equation? This leads to the third and most profound level of speculation. What if the difference in dynamics is not just about the type of gas, but about the internal structure that channels it? We assume the nucleus is a single, consolidated body, but what if it is a loosely bound assemblage of smaller fragments, a rubble pile with a unique cohesion? The outgassing of carbon dioxide, potentially more explosive and pervasive at lower temperatures, could be acting to gently torque this assemblage, causing subtle shifts in its rotation state that in turn alter the net direction of the thrust. The non-gravitational acceleration would not just be a function of solar heat, but a complex feedback loop between the heating of the surface, the release of gas from the interior matrix, and the consequent mechanical evolution of the body's orientation. Could the very forces that propel it through space also be slowly reshaping its internal configuration, making its motion a window into its fragile and evolving structure? The significance of these detailed observations extends far beyond this single object. The unique spectral signature of 3I Atlas, its specific ratio of carbon monoxide to carbon dioxide to water, is more than just data. It is an interstellar fingerprint. When the Vera C. Rubin Observatory's legacy survey of space and time begins its relentless scan of the sky, it will discover thousands of new moving objects. Most will be familiar asteroids and comets from our own system, but hidden among them will be the next interstellar passerby. How will we identify it quickly, with only a few nights of data, before it recedes into the darkness? The answer may lie in the lesson of 3I Atlas. Machine learning algorithms can be trained to recognize the subtle, early signs of non-gravitational acceleration, the specific color indices, and the rate of brightening that distinguish a volatile rich interstellar object from a native solar system body. The fingerprint of this visitor provides a new template, a new category for these algorithms to search for. We have moved from a definition based solely on orbit to one that can be informed by composition and behavior. The voice of 3I Atlas has given us a new search query for the galaxy's silent traffic. But if this is the first of its kind we have studied so closely, how many other voices are there in the dark, each with a composition telling a different story of its origin? And as we learn to classify its nature, we must also confront the most provocative of the early speculations, the one that captured the public imagination before the data had fully spoken. The unusual composition, the hyperbolic trajectory, the very mystery of its origin, could these be signs not of a natural object, but of something else? The steady, unfluctuating brightness curve, devoid of any sharp, periodic spikes that might suggest reflected light from polished metallic surfaces, argued against an artificial construct. Then came the crucial campaigns of September and October 2025. The coordinated efforts of the Deep Space Network and other radar facilities, listening not for a whisper of a signal, but blasting the object with powerful radio waves, yielded no echo that betrayed a manufactured structure. There was no modulation, no signature of technology. The European Space Agency and NASA released concurrent statements. The object was natural. It was a comet, albeit a strange one. The dream or the fear of a visiting craft was laid to rest by the relentless consistency of physical law. Yet, in dismissing the most sensational idea, have we perhaps closed a door too soon? For if this is a natural object, its very naturalness, its profound strangeness, tells a story that is in its own way far more staggering. It is a piece of a foreign world, a fragment of another system, carrying within its dark heart the unaltered conditions of its birth around a star we have never seen. What secrets of galactic planet formation are locked within its cryptic, carbon-stained core, and what will its continued dissection reveal about our own place in the cosmic tapestry of matter? The data has confirmed it is not a ship, but perhaps that makes its journey all the more significant.